Hello everyone. Let's talk a little bit more regarding the Serway book, the Serway and Vuille book, 11th edition, often called the Serway book, just in our colloquial language, speaking about the whole matter. We had done chapter 16 the last time we had gotten together and filmed this, and I'm going to go back to chapter 16 and hit two problems that I had not done. I know I had said I would do 66, and I ended up not filming it. Ran out of time a little bit, so let's do it. Let's do that right now, or at least in the very near future. We'll do problem number 66 from chapter 16. But before we do that from chapter 16, we'll do 61 from chapter 16, and then go to chapter 17 and do these problems. Very many of these problems are going to scroll at the end of the films that we do. Now, we already had a lot of things scroll in the last film regarding chapter 16. And so we already had a lot of things scroll, including 66. 61 was not something that I had actually posted in handwriting. So you'll see it here, and that should be good enough for us. And that won't be scrolling. You won't see it having scrolled in the chapter 16 discussion. I always call these chapters, and yet Serway and Vuille calls them topics. Topics, and topic 18, topic 17, topic 16 is the same as, saying topic 16 is the same as saying chapter 16. So I'm using the word chapter, but Serway and Vuille use the word topic instead of chapter. They are synonymous for all intents and purposes, guys. Mean the same thing. So, saying all this, let's talk about topic 16, number 61, and we'll take it from there. So topic 16, which is chapter 16, as we've said, problem number 61. Problem number 61 says, a parallel plate capacitor with plate separation small d has capacitance C sub 0 in the absence of a dielectric. A slab of dielectric material, a slab of dielectric material of dielectric constant kappa and thickness d over 3. Now wait a minute, I think we already, that one I think we already did, guys. We had done that one, had we not? We may not have. We may not have. Either way, let's just do it. Let's do it again. Before we do, I think there was the other problem I wanted to look at, and that was problem 59 right before that. So forgive me, guys, for some reason. I don't know how I forgot to even put that up there. But again, this one's not there. So let's, it's kind of, I started this thing in a little bit of an awkward manner, but that's all right. We'll straighten it out. So 61, 66, let's go 59, 61, 66, and we'll see what we got. We'll go like that, guys. And I had read problem number 61 regarding that, so let's take a look at it. I don't think I had, for some reason, I don't think we ever had gone that way in the actual problems that I was doing. So there's going to be two extra ones here, and you're not going to see them scroll at the end in the regular handwriting with which I've done these, because I've sort of decided, sort of at the last minute, to kind of do these two. So we'll do them live, more or less live, in the filming of this, and we'll take a look at it. 59, 61, 66. Let's do problem number 59 first. I know I'd said 61, and we'll get to it in a second, but for problem number 59, 3 parallel plate capacitors are constructed. 3 parallel plate capacitors are constructed, each having the same plate area, capital A, and with C1 having plate spacing D1, C2 having plate spacing D2, and C3 having plate spacing D3, show that the total capacitance C of the 3 capacitors connected in series
is the same as a capacitor of plate area A with plate spacing D equals D1 plus D2 plus D3.
All right. Guys, we know, vis-a-vis that stuff, kind of keep our minds into this thing, I guess you could say. When we're talking about capacitors in series, for capacitors in series, we were able to derive, and that keeps going, plus 1 over C4, plus 1 over C5, plus ... plus 1 over Cn. So we know that. We've seen this. Plus ... plus 1 over C sub n. So that's if we're talking about something in series. Something to kind of keep in mind when we're doing any of this work. When we're talking about parallel, if the capacitors are in series, this is how you can find the equivalent capacitance. If the capacitors are in series, this is how you find the equivalent capacitance. If the capacitors are in parallel, however many there are. I mean, there might only be 2 capacitors. Why am I adding a third? I'm saying hypothetically there might be very many. So on and so forth. They're basically saying let's say you got 3 capacitors and they're in series. One of the capacitors has capacitance C1. It's got a separation, plate separation, D1. So C1 capacitance, D1 separation in the plates, area is A. The second capacitor also has area A. And the third capacitor also has area A. So that's not an issue. As we look at this, we've already derived this, we've looked at it. E naught A over D if you're talking about 2 parallel plate capacitors. So true. What does that mean? That means that C1 is E naught over A1, and A1 is just A. They all got the same area. D1 is the separation on that one. C2 is E naught A over D2, and C3 is E naught A over D3. Great. Let's put these guys in series. We're not, it's not quite as easy. If it was parallel, it's a little easier discussion, perhaps, depending on what conclusions you want to actually draw, right? But we're trying to prove that it's the same at the end of all this. The capacitance is going to look like this. Capacitance is going to look like that, and we're being asked to say that D is going to be D1 plus D2 plus D3. So they want to prove that if you take these 3 capacitors and put them in series, these three capacitors described by this mathematics, these 3 capacitors put in series are going to have the same capacitance. Well, here's the general rule for the capacitance for 2 parallel plate capacitors. We've gone into this, pretty neat formula. If that's the case,
we got to prove that that capacitance is going to be E naught A over D, where D is equal to this. What is we got to show? If we do this, we're in good shape. We can just show this. Well, we know that we're hoping we draw this as a conclusion. The resultant capacitance is going to be equal to this. Okay. Well, based on what we know about series, we're not using parallel, we're using the series one. We're using the series equation, not the parallel equation. We know that 1 over C is going to equal 1 over C1 plus 1 over C2 plus 1 over C3. Which is what? Well, 1 over C is going to equal E naught one over E naught A over D1, C1 on the bottom, C2 on the bottom here, C3 on the bottom here, and we're looking okay. All right, we got to make it look like that. Let's erase this. We know what we're looking for. For some reason, guys, I thought I had another eraser here. And of course, it's right in front of me. All right, so we're looking at that. We care about the one pertaining to the series. Got this right here. We're, like I said, hooking back to chapter 16, 59, 61, 66. We're going back to chapter 16, 59, 61, 66, then we're going to go to 17, these right here. So let's see what we can do. What do you got? What you have is 1 over C is all that. So we got 1 over C. 1 over C equals the 1 over C equals the reciprocal of this. 1 over C equals 1 over that right there, which is D1 plus 1 over this plus 1 over this so we got this. Should be pretty clear, guys. I just want to make sure. I can't really see the stuff, the film, until after the fact. What does this all mean? Well, let's not try anything fancy just yet. Leave the 1 over C alone. We have common denominators here all over the place. So add the tops and keep the same common denominator. If these are equal, their reciprocals are equal. Absolutely. That right there, bounded by the red, is the same as this right here, bounded by the green. That's what we're trying to prove. So that's problem number 59 from chapter 16. '61, I had started it last time. Let me start it again. Let's do it. For problem number 61, a parallel plate capacitor with a plate separation D has a capacitance C sub 0 in the absence of a dielectric. A slab of dielectric material of dielectric constant kappa and thickness D over 3 is then inserted between the plates. Show that the capacitance of this partially filled capacitor is given by, and they got a particular formula there. Treat the problem as two capacitors connected in series, as in the figure that they described to us, and then just kind of prove things the way you want to have them proved. Okay, shouldn't be too bad, guys. Shouldn't be too bad at all. But again, some of the, with caution, we look at this and I think we get through it okay. Okay, so what they're saying is, they're trying to say here, let's write this out so we know where we want to go with the conclusions, actually. So for 61, there's a parallel plate capacitor. There's a parallel plate capacitor with a plate separation. Let's see how we want to do this. There's a parallel plate capacitor with a plate separation D, and it has a capacitance C sub 0 in the absence of a dielectric. So a parallel plate capacitor with a plate separation of D has a capacitance C sub 0. So C sub 0 is what the capacitance is when there's a plate separation of D in the absence of a dielectric. We know from a lot of things that we've already talked about, that's going to be the capacitance in the absence of a dielectric for that particular circumstance, for the circumstance of a parallel plate capacitor with a plate separation of D and has a capacitance of C sub 0 in the absence of a dielectric. A slab of dielectric material of constant K and thickness D over 3 is then inserted between the plates. Show that the capacitance, they're asking you, when they insert the dielectric of thickness 1/3 the plate separation, it's not D. D is the plate separation, but the dielectric is D over 3 in thickness, 1/3 D in thickness, and kappa is the dielectric constant. They're telling us, they're asking us or telling us, prove kappa is the dielectric constant under consideration. This will be the new capacitance if you're working with it as this. So we're saying they're giving us this initially, and that's without any dielectric or anything between them. And they're saying after you put a dielectric between the plates. Here you don't have a dielectric between the plates. But afterwards, after you put a dielectric between the plates, They're claiming that the new capacitance is going to be what the old capacitance was times that ratio right there. That will be the new capacitance. Now, we are going to work under the assumption that whenever you do something like this, it's as though you're doing two. They're saying pretend when they insert that, and they're saying, the material's got the same base area as the plate does. We're making that assumption. To my knowledge, they didn't really say that here, but that's the assumption that's given, and that's the way it's drawn in the book. If we look at the book, they're saying, okay, there's two parallel plate capacitors, one plate above the other, and then that yellow material, that yellow slab, is every bit as much surface area as each one of the plates has, but it's not as thick as the plate separation. Each plate has an area of A, the slab also on a surface area. Surface area of each plate is A, surface area of the slab, the dielectric slab, is also A, but it's D over 3 in thickness, whereas the separation of the plates is 3 times that. It's D in thickness. The distance between them is D. And you put a dielectric slab in there, which is 1/3, which has a thickness which is 1/3 the plate separation. So D over 3 is the thickness of the slab that's been put there. How do you want to play this? Well, the way you got to do it is, they were saying essentially what's going on is, there it is, and it was looking like this, guys. Let's try to, again, this is not going to be any sort of work of art, that's for sure, but here we are. So we got this, and we know that's D. And they're essentially here's the slab, the dielectric slab, dielectric constant kappa, and 1/3 thickness. So this is 1/3 times D, and this right here is 2/3 times D. Okay. As far as the thickness is concerned. So that's the situation here, and they're saying, okay, this is what just happened. And they're saying, look, the way this can be modeled, guys, is that this right here and this right here, you can model it as the slab constituting its own capacitance, the slab constituting its own capacitor, being its own capacitor, and the empty air, that also being its own capacitor. So looking something like this. I mean, not any kind of work of art here, guys, but again, this is kappa, and this is kappa. So you could kind of view it as, this is capacitor C1, this is capacitor C2, this is the resultant capacitor, and you can model it. This resulting capacitor is the same as this when you put these together. Yeah, good enough. I mean, we can certainly say that, because the voltages add up. The charge has, so at the end of all this, what do we say about how we actually ended up proving this? When we're saying this, let me just try to think about it for a second, guys. Right, the charge was the same. So the charge associated here and charge associated there is the same. Charge here and charge there are going to be the same. So there's justification for going that way, is the argument that they pretty much give to us when we're talking about something like this. If that's the case, these guys are in series. We got to, at the end of the day, guys, we've got to make it work. We've got to make it work, and it's got to come out to this. So we'll see what we can say. We know this guy right here, if they're in series, the voltages add up, but the charges don't. The charges are identical, only the voltages are adding up. And the way that's going to happen is when you got, essentially that's where that's why this works. Because the voltages add up to the total voltage, whereas the voltages add up to the total voltage, but not, but the charge is the same. So we got this right here. Well, how's that work? It essentially works like this. You've got 1 over C at the end of the day is going to be equal to 1 over C1. Now remember, this is 1/3 D for distance. The area is A, the epsilon naught is epsilon naught. This is 2/3 D. The area A. A doesn't change across the board. A is everywhere. Epsilon naught is everywhere. This is 1/3 D. This is 2/3 D. That should get us there. What we got is, they told us, this is before you put the thing in there, if you want to put a dielectric in there, we said that the capacitance increases by that same factor. So you got, the symbols tend to repeat enough that they could they're helpful, and at the same time they can also be a little confusing. As a general rule, guys, dielectric's going to increase the capacitance, is what the argument is. Dielectrics tend to do that. So there was just to check, guys. Yeah, it's not a problem. Kappa epsilon naught A over D. So that's how we're going to do it. Yeah. So that's just something to keep in mind. Okay. Let's keep it in mind pretty well then. Here we go. Here's C sub 1. C sub 1, this is what the general look is. C sub 1 is going to look like this. The D for plate separation is D over 3 in this case, and this is C sub 1. This is C sub 1. So what happens here? Well, you put them closer together as a bigger capacitance, is what it means. This is going to make it a bigger number. You end up getting 3 kappa epsilon naught A over D. The D was, like I said, the D was here. Do the division, flips like that, you got this. Really? Yeah, absolutely. So you got 3 kappa sounds good to me.
What's the other one? The other one's just the way we're used to seeing this stuff look. Epsilon naught A over D. Yeah, the D is something different though. It's 2/3 D. For the C sub 2, it's going to be everything we've seen in the past, you guys. But rather than a D, you got 2/3 D. 2 times D divided by 3, or 2/3 D, doesn't matter much. But that's what C2 is looking like. What's that all about? C2 flips around the right way. 3/2, the 2/3 flips. Look, there's a lot here. There's the epsilon naught. There's the epsilon naught A over D. Yeah. This epsilon naught A over D is kind of more or less the standard. This 3 kappa multiplied with that. This 3/2 multiplied with that. But the epsilon naught A over D, okay, it's the hardest part of the whole problem. Guys, once we get there, this C2, yeah, this is where it's going to go, and that's it. The rest is the formality of doing the mathematics carefully and getting the right answer. The rest should go pretty quickly. The rest should go pretty quickly when we do that. So that's essentially the argument, you guys, how we're going to play the whole thing. We have to confirm that it's going to come out to this. Yeah, remember now, C sub 0 is E naught A over D. We've seen that so many times. That's C sub 0. Got it carefully. They're making the claim before you did anything to this thing. It was the standard equation for the capacitance between 2 parallel plates. What is that? Well, capacitance is E naught A over D. Absolutely. E naught A over D is the standard capacitance. That's what it would have been before you did all this business over here, guys. So that's the original C sub 0 that was on there. Okay, we got this. What does that mean? Well, that's the end of the road to the C. E naught A over D is the C naught. This is the 3/2. Again, E naught A over D. E naught A over D. Yeah, sounds about right to me. Tell you what.
pull 1 over C naught out of here. Is that true? Yeah. The math is valid. The math is definitely valid, guys. Again, the C naught was E naught A over D. That's the standard. And they told us, go with the standard before you do anything to it. Before we insert the dielectric slab there, before the dielectric slab is put in place, it is just E naught A over D. Sounds good to me. I'll call it C naught. They called it C naught. Let's call it C naught. And the rest is just figuring out how to do something like this. How were we able to actually do this? Okay, so what we can say is, again, we said this guy right here is C naught. This guy right here is C naught. 1 over 3 halves C naught plus 1 over 3 kappa C naught equals 1 over C. That's all I'm saying right there, guys. Let's get that very straight. Again, I keep forgetting, guys, you can always go backwards with this. You can always speed this up a bit. If you already know the stuff pretty well, you speed it up, or you could go backwards and the whole thing at all. You can go backwards and look at something again, or speed it up and go forward if you're following the stuff pretty well. So I think we're in pretty good shape, guys. We're looking at this right here. What is this? Well, there's a lot going on. It's more formality than anything else, guys. I think we're so much closer to this than what we might think when we initially look at it. This is 1 over 3 kappa. 1 over 3 halves is 2/3. You know, and I'm almost, kind of arguing with myself where to go with that. Okay, that'll work. What do you say you multiply 3 kappa, looks a lot like 3, if you just go kappa over kappa times 2/3. If you multiply 2/3 by kappa over kappa, this guy stays as is. Kappa over kappa what do we got here? Why don't you add these together? Got a common denominator is what you got. True. All right, if two things are equal, their reciprocals are equal. The reciprocal of a product is the product of the reciprocals. The product of these two factors get the reciprocal of each of these, and when it flips, you are done. C equals flip this. Flip them, flip everybody upside down. You're done. And that's what we're trying to say there, guys. Yeah, that's what we were looking for, guys. All right, that's 61. Let's go to 66. And this is the third problem from topic 16 that I'm just hooking around and doing again. Didn't quite have the time last time. We covered quite a bit of stuff last time. So let's just kind of square this away as we do this. Problem number 66, also from topic 16. Just as 59 and 61 were from topic 16. 66 is the last one I'm doing from topic 16, you guys. A spherical capacitor consists of a spherical conducting shell of radius b and a charge negative q, concentric with a smaller concentric sphere of radius a and charge q. One's got negative q, the outside one's got negative q on it, and the inside one's got positive q on it. What are they saying here? Basically, they're saying A and B. Find the capacitance of this device. B, show that as the radius b of the outer sphere approaches infinity, the capacitance approaches A over K sub E equals 4 pi epsilon naught A. So let's see what they're saying here, guys, when we do this. All right, guys, so they're saying here, you know, there's a spherical capacitor, and there's a number of ways you may want to look at this. So let me just make sure I'm agreeing with everything I'm doing here, guys. We know that, remember how we did the parallel plate capacitors? Remember how we did the parallel plate capacitors, you guys? We were able, for the parallel plate capacitors, we said, okay, wait a minute, there's an E field produced by one of them, and there's an identical E field produced by the other one, and we're going to add them together, and in that particular instance, at least in that particular instance, they, the potential, the E field we're talking about and everything else. So, how does this play out? How does the potential? We talk about the E fields and we talk about potential. Well, to find the potential, we had to talk about the E fields at some level, right? And we knew that the E fields, there was a contribution. There was an E field from one of the plates, and there was an identical magnitude and identically directed E field. They weren't like from the same place, but they basically were. There were E fields. There was an identical E field produced by one of them as was produced by the other, and so they augmented each other, and the sigma over 2 epsilon naught plus sigma over 2 epsilon naught gave us sigma over epsilon naught, right? 2 times the quantity sigma over 2 epsilon naught is sigma over epsilon naught. So kind of the argument they're giving here, they're saying V due to the inner shell. So you say, the total potential is V due to the inner shell The other one's V due to the outer shell. Now they're going to add up together and they're going to kind of augment each other, as we've talked about in the past in instances such as these. How's that going to play out? Well, they're saying for the inner shell, that's K sub E, K electric, that they're talking about. I'm using K, it's not kappa, it's K, which is the same as the K sub E. K sub E is what they say in the particular problem. KQ over R, and they're saying see what that is here, guys. Where R equals A. I should have, just easily use the A here on this one. But so where are they here? How's this whole get? Now there's the augmentation's not going to happen like that. But let's see, because how hard are they pushing away? I mean, the Q, the positive Q, is going to resist bringing a positive charge into the matter, but the negative Q is not going to resist it. So there's a bit of a tug of war there. It doesn't quite play out the way we've played it in the past, so kind of be aware of that. So we got negative Q here. So what's going on here? That comes out to one over R minus 1 over B. The R happens to be equal to A. That's the radius of the smaller sphere. So it's coming out to here. So, here we go again. The stuff gets called different things, different places, I guess you could say. Let's kind of speak their language, I guess you could say. The sign does play a role here. And if something was coming in from infinitely far away, let's say it was a positive charge being brought in, another positive charge, a positive test charge being brought in from infinitely far away, this much work would be required to do it over here. Yeah, but on this side, it's being drawn to it. So it's not like it's going to need a positive amount of work to bring it in there. This is already bringing it in. The difference between the two, in other words, if there was a charge coming in from very far away and you were trying to bring it in there, you'd have to fight your way to get to this point to have this much potential. You have to fight this much to be able to do something like that. And the positive test charge. So this would play a role in the potential, but when there's a negative charge present, it already wants to bring it in. So it's not as hard of a fight as you might think it is. That's why there's a subtraction. That's why there's a subtraction there, you guys. So you got this. Here we go with the language again. I mean, they've been using delta V, and that's actually, honestly, probably the best way to use it. Delta V, the change in potential between the two. Sign matters. It's not a vector quantity. Doesn't matter the path that particle coming from infinity is going to take to get in there. Wow, what do you mean? It went really, really far away. Yeah, but it was going sideways. So it really wasn't taking any energy to get that way. When it went head on into it, that's the only thing that counts. And no matter how you go about doing that, it's going to be the same number, same answer. So you look at this, you say, okay, KQ, like I said, I use the V in place of delta V. I use them synonymously. Be aware of the language that somebody's trying to speak regarding that. Hopefully, I've made that clear. Using their language, let's use their language. There it is. You got this. Add these two. B over A. I'm sorry, multiply 1 over A by B over B, multiply 1 over B by A over A, and you end up getting let's see that. Yeah, absolutely, absolutely. And from there, A is equal to, for A, problem A is saying find the capacitance. Problem A is going to be equal to the capacitance, at least the solution is find the capacitance. The capacitance is Q over V. So Q over V or Q over delta V. Delta V is probably the better way to go, like if you really want to be strict with the language here. What do you got? We've got Q. We got delta V is KQ. B minus A over AB. The Q's cancel. The AB goes up top. There had to be a K here. Yeah, there was. I'm sorry. And there you go, guys. That is the capacitance of that spherical capacitor. That's interesting. So, what do you say? Well, I mean, you could do a bunch of things here. For B, they're saying what happens if you're talking about A staying the size it's at, A staying the radius that it's at, and B becoming very, 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 very big. B goes toward infinity in a sense. I'm going to use that equation and maybe and hopefully pull it off that way. So what you can say for B, C equals AB over K, the difference B minus A. If B is a lot bigger than A, if B is a lot bigger than A, B minus A is about equal to B. Therefore, B minus A is about equal to B. K is K. This is about B. B minus A is about B. The B's cancel. Approximately speaking, it's going to come out to A over K, which is, that's KE, not kappa. The K and the KE Let's get it straight. I mean, this is the K, which is the same as KE, just to be careful. And that's 1 over 4 pi epsilon naught. So what do you got? You got A over 1 over A over this is, let me just see how they wrote it. Okay, yeah, it's, A over this is 4 pi epsilon naught A. And that's the story. And that's what they're trying to say, guys. And that's, I think, just confirm that. It should be, it certainly is going to be the conclusion I think they wanted us to get. And there it is. Yeah, they wrote it a bunch of different ways. 1 over K sub E equals 4 pi epsilon naught A. That'll work. As I said, guys, the K that we're used to seeing, you got to watch out. It looks like a kappa, and that can get us in trouble. It looks like a kappa for the dielectric. So we know that. I mean, we come to here, do all the math games that we need to do, and we're fine. We're fine. Sounds good. Okay, that was just some stuff I wanted to clean up on regarding chapter 16. The last time we got together, the circumstances were such, I wasn't really going to have the time to do that. But now we did. Now we did. So we were able to do this. See what else we could say here, guys. Well, what we can say is, for chapter 17, the problems that we had mentioned, I had them on the board, guys. I erased them. But you can, like I said, we can always go backward with all this film, guys, and see what's going on. That's kind of the real nice thing about it, I guess you could say. Let's see what we have here. And let's see what we can say regarding current and resistance and things of that nature. Okay, so there's a number of things that get said. Let me say, let me summarize them a bit, guys. By no means is this what I do on a lot of these things. By no means is it the most exhausting of all lectures that you're going to find, most exhaustive of all lectures that you can do on this stuff. But at least points us in some directions, and we're reading the material. And like I said, as soon as we're in contact with one another on a basis where we're talking more person to person, it's going to be a lot easier. And that's, again, some of the challenges that have been going on as we speak now for more than a year now. May things be better for everyone. So, but right now, let's give some basis to what we're doing here. When we go to chapter 17, there's a few things to look at, and of course, then there's the problems that I wanted to talk about as well that I think are going to make a little bit of sense to us when we're doing this stuff. Once we can do the problems, guys, we understand a lot of what's going on. All right, so for 17, you guys, I mean, they talk about current. We're always making the assumption when we talk about current that we're talking about positive particles flowing. The mathematics, the directions are set up in such a way that we're talking about positive particles, how they would flow, and given if there's a potential difference that they can go through. If there's a potential difference, there's the potential for work to get done if there are charged particles present. And work will be done if there's a potential difference. So with that in mind, you guys, I mean, we could say a whole lot of stuff. So how actually are you going to play this thing to actually do it? Well, they're telling us that the average current is the amount of charge that passes through a particular cross-section of wire per unit time t. If you take per unit time delta t, if delta t approaches 0, you got this thing called dq dt. It becomes a calculus problem. They're not going there in this book, nor are we. But just for the sake of looking at this, current is the time rate of flow of charge through a surface, through a particular cross-sectional area. And they bring it, they don't really tell you that it's this, but in the limit as delta t goes to 0, you got dq dt, which is a classic calculus problem at that point. They're telling you that the current in a conductor is related to the motion of the charge carriers, which is pretty strong stuff. They're saying I is equal to the number of mobile charge carriers per unit volume. I equals N, which is the number of charges that can move and that are moving in some sense or another. The amount of current, and this is coulombs per second. Coulombs per second, coulombs per second. The current in a coulomb, 1 coulomb divided by 1 second is called 1 ampere. The amount of charge passing per unit time, the current, is equal to the number of free charge carriers, where N is the number of mobile charge carriers per unit volume. This is the number. So it's not just the number of charge carriers, it's the number of charge carriers per unit volume. You might have a very voluminous situation going on, and I know how many charge carriers are present for for every small portion of volume. I mean, I may have 1,000 cubic meters under consideration there. 1,000,000 cubic meters. I want to know how many, but I know that they told me, hey, I've got this many charge carriers per cubic meter, per 1 cubic meter. Well, how many would there be in 1,000,000 cubic meters? Multiply it by 1,000,000. Okay. So I is, as we said here, I is the current. N is the number of mobile charge carriers per unit volume. Q is the charge, the amount of charge on each carrier. And V sub D is the drift speed of the charges. How fast are the charges moving in the particular direction because there's an E field present, because there's a net E field present, and there's a potential difference, and they're going to go that way. Correct. True. And A is the cross-sectional area that they're crossing. See, if there's a lot of area to cross, and they're moving that fast, that is a lot of current. That plays a role right there. So that's pretty important stuff. A lot you can say. Let me try to abbreviate some of this stuff, guys, for the sake of getting into the problems themselves. All right, we got what we got. So, this is interesting. The current I in a conductor is related to the number density N of charge carriers per unit volume, the charge Q per carrier, the drift speed V sub D, and the cross-sectional area of the conductor. There's got to be a net. We have the V sub D is the resultant that is going to be going in one particular direction. And we're making that assumption that somehow at the end of this, there is going to be an amount, and that V sub D is a vector quantity, and it points directly in the direction of the flow. Now, there's going to be particles moving all over the place, potentially backward, forward, up and down, but the net situation is going to be V sub D as a vector moving in the direction of motion, in the direction in which the current is flowing. I guess that's essentially the argument that you're trying to construct here. There's voltage, resistance, and current. There's a lot of ways to view this, guys. Potential difference, it's associated with voltage, I guess you could say, is one and the same. Delta V or V. Now, you've heard me use V. You've heard me use delta V. This is kind of interesting. The amount of potential difference between two places is directly proportional to the product of the amount of current and the resistance. Resistance is actually going to try to prevent the flow of electricity, if you will. If there is a great R, a large R, a lot of resistance, and there is a lot of current, despite the fact that there's a lot of resistance, and you still got a lot of current. This hose that's being used to put out a fire, wow, it's not working that great. It's resisting the flow of the water, and yet there's still a lot of water coming out. There has to be tremendous pressure for that to happen. Well, the potential difference is kind of like the pressure on the whole matter. The potential difference is a measure of the capacity to do work per unit charge. And if this is if there's a lot of current, despite the fact that there's a lot of resistance, big times big is a big answer, and you get that. That'd be one way to look at it. Another way you can kind of look at it is this. Well, why don't you just divide by R on each side? And you got delta V over R. If something is going to give a lot of potential difference, a lot of tendency to want to move charge, and there's not much resistance at all, big divided by small, there's going to be a lot of current. What if there's not a lot of potential for charge to flow, and there's a big resistance? Small divided by big is small. Of course, it's going to be a small amount of current. So you could kind of play with all three of these. It's kind of it's something pertaining to this thing that works very, very often, very, very many circumstances, called Ohm's law. These are all, one is born of the other, you guys. I could multiply by R on each side here. I use V a lot of times and not delta V. Okay, and you see that in some of the notes. Just be aware of that. I mean, that's kind of a matter that you just, again, be aware of it. That's all. Is that true? Yeah, big resistance would occur when this happens. There's a lot of potential energy available for flow to happen, and yet there's only a little bit of flow. Little bit of flow of charge. Big energy capacity, potential for energy to flow, and yet only a little bit of current flows. What's stopping it? A lot of resistance. If delta V is big and I is small, big divided by small is huge, big resistance. What if there's not a lot of let's say there's not a lot of potential not too much potential for something to flow, and yet there's a big current anyway. That means small divided by big is very small. You still get a lot of current. Resistance is small. Resistance is small. This is all kind of a takeoff. All of these sort of are a takeoff of Ohm's law, you guys. They're a takeoff of Ohm's law, what goes on there. If a conductor is long and does not have a very big cross-sectional area, that affects the resistance also. So R equals the Greek letter rho times the ratio L over A. What's going on there? You could have the exact same material, exact same temperature, exact same everything going on, except for something else going on. And that is the cross-sectional area of the wire might be a lot bigger in one instance as compared to another example in some other instance. And it might be a longer wire or shorter wire or whatever. Rho is the resistivity of a particular material. Rho is the resistivity of a particular material. L is L, A is A. What do we have here? Well, it means this. For a particular resistivity, if the wire is really, really long, it's a big number on top. And if the area, the cross-sectional area is really, really small, what's something really, really long here, which would be really, really long, meaning a great size number, divided by a small sized area. Big divided by small is huge. Wait a minute, if it's a really long wire and does not have a great cross-sectional area, that times rho will give you a big resistance. The resistance is going to be bigger. For the same material, if it's a really, really long wire and not a big cross-sectional area, L over A is a big answer because L is long, meaning big answer. A, the cross-sectional area is small, meaning small answer. Big divided by small is huge answer. So it'd be big that way. Less resistance if the wire is short and it's got a big cross-sectional area. It lets stuff get over there. This would be small, this would be big, divided, it's tiny, small resistance, relatively speaking. They're saying for this stuff right here, you guys, you look, and they say also for resistivity, over a limited temperature range, the resistivity of a conductor varies with temperature according to the following expression. There's more resistivity, hence more resistance for a material, all of the things the same. If, got the one right here, it kind of standardizes the whole thing, plus alpha. Alpha is the temperature coefficient of resistivity. T is the temperature you're talking about, right? In Celsius, degrees Celsius, because you're getting a difference. So it could be Kelvin or Celsius. The bigger the temperature, it's harder to flow. Lower the temperature, easier it is to flow, according to the equation here, how it plays out. That being the case, you guys, for all other things equal, if I put an L over A right here and an L over A right here, that's just saying this, and that follows pretty good. Put an L over A, you got rho L over A, rho 0 times L over A, that's R0. Multiply by L over A on this side. Multiply by L over A, multiply by L over A. L over A times rho is R. L over A times rho sub naught is R sub naught. That's where they're getting this, you guys. And they talk about different things, guys, and we'll talk about them as well. I mean, but Okay, guys, so we see a lot of stuff here. If, you know, this thing about potential and everything else we talk about, you know, delta V is equal to, delta V is equal to the work per unit charge. You know, remember the potential, remember it's kind of analogous to other stuff that we've said. I mean, talk about that. I don't like to erase any of this, but let me erase some of it. So we can always come back to it. You know, like kind of like we said what E was all about. E was, you know, force per, you know, E is force per unit charge. V, or delta V, let's stay with their notation, is work per unit charge. Let's talk about that. Work is Q delta V. True. Work divided by time, Q divided by time. That's delta Q over delta T. That's I. Work divided by time is power. Say, my notation, it's not my notation, other people have used it. I use IV. I just say IV rather than I delta V. No big deal. Just remember what's what. Didn't we say that delta V? You know, we looked at this, we said a lot of stuff. We said, yeah, I mean, we said delta V was IR. Okay. Put an IR here. Put IR here. IR times I. That's the power dissipated through resistance. You got to look at the circumstances in which something's being asked. Okay. So on and so forth. So they come from the same place. Isn't I delta V over R? According to the math? Put that in here. Over R squared times R. Well, R squared underneath times R over here, they'll cancel. So you get to that. So on and so forth, guys. So you got something like this. And we look at the circumstances in which something can be done like that. I mean, how this stuff works out. See exactly, you know, like I said, there's a lot of ways to look at this stuff and how we interpret things. Again, when resistance is literally in the equation, I mean, we can do some stuff and relate it to resistance, in addition to everything else that's going on. But generally there's going to be some resistance. There's current, and there's voltage, and there's potential difference. And that's kind of what we're talking about here. All right, guys. So pretty fascinating stuff. I mean, we went, from a microscopic point of view, we went right here, and pretty fascinating stuff that goes on, even for that right there, especially for this. I find it's remarkable, and you'd be surprised. The speed doesn't have to be that great because there's just so much surface area that's being crossed by so many particles, so many charged particles, so much surface area. It's still a tremendous amount of current, and the drift speed is remarkably slow oftentimes. Okay. All right, let's take a look at some of this stuff, you guys. Based on what I just said here, it's that, we looked at some things, and let's see exactly how we want to talk about it. Let's look at problems 2 and 4. Let's start with 2. We'll kind of take it from there. Okay, so all right, guys, problem number 2 from topic 17. A copper wire has a circular cross-section with a radius of 1.25 millimeters. If the wire carries a current of 3.70 amperes, find the drift speed of the electrons in the wire. Take the density of the mobile charge carriers in copper. To be N equals 1.10 times 10 to the 29th electrons per cubic meter. That's a lot. B, for the same size wire and current, for the same wire size and current, find the drift speed of electrons if the wire is made of aluminum with N equals 2.11 times 10 to the 29th electrons per cubic meter. There's nearly twice as many electrons associated with the aluminum as there is associated with the copper. So if there's twice as many electrons, you probably need half the speed, right around that ballpark. So let's see what's going on. That's where we're going to look at it. All right, we've talked about a lot of this stuff. Not in the greatest of detail yet, but we've talked about it. We know what we need to know. That's what we need. Makes it pretty easy. What's that going to be? V sub D is going to be whatever the current is. Make sure that all the units agree. V sub D is going to be I over NQ A. Absolutely true. Make sure everything's MKS system of units. Make sure it's the SI system of units, because the ampere is the SI system of units. You plug in all the numbers, make sure everything's converted to meters, to seconds, to meters squared, meters cubed, etc., etc. And they gave you the numbers. Plug in all the numbers that they gave us, guys. You should see this. And I've got the numbers and the stuff that's going to scroll by you at the end. At the end of this video, this will scroll. At the end of the film, the solutions from topic 17 are going to scroll. The ones I had, some that I've done and some that I've not done, actually. But all of them are going to scroll by there that I had under consideration. These, including these that I'm doing live. Not doing all of them live, as we said, guys, but we're doing a good amount, I hope. All right, we got it to here. Yeah. Well, my gut feeling was they didn't change anything with the aluminum one. The other one was, did they even say what it was as far as the material? I think it did. For some reason, I'm remembering copper here or something. No, they're not. They're not saying anything. Oh, it is copper. Copper, actually. So they did say copper. The other one's for aluminum. Almost twice as many. For everything else going the way it's supposed to be going, if this N is twice as big for the aluminum as it was for the copper, if this is twice as big, V sub D is going to be half the size, on the order of half the size. You plug in all the appropriate values, indeed it'll be just that. And again, this will all scroll at the end, you guys. 4. A typical lightning bolt may last for 0.200 seconds and transfer 1.00 times 10 to the 20th electrons. Calculate the average current in the lightning bolt. Well, it doesn't last that long, but when it is lasting, during that time period, when it is actually occurring, how many amps is that thing? A typical lightning bolt may last for 0.2 seconds and transfer 1 times 10 to the 20th electrons. Calculate the average current in the lightning bolt. It's Q over T, delta Q over T. We can speak the language a lot of ways, guys. What's going on here? What's the amount of charge? Tell you what, let's find the amount of electrons first. It's going to transfer this many electrons. It's going to transfer this many electrons. Now, it's not running for a long time. I mean, it's not, Let's knock the mathematics out of here. We got to put on there, on average, right? Just for that duration now, right? It's not a long duration. 1.6 times 1 is 1.6. 10 to the 20th times 10 to the negative 19. 1.6 times 10 to the negative 19 coulombs per electron. That's the charge per electron. 1.6 times, 10 to the 20th times 10 to the negative 19 is 10 to the 1. 1.6 times 10 to the 1 is 16. 16 divided by 0.2 is 80 amps. Yeah, that's something. That's remarkable. A wire of diameter 0.8 millimeters and length 25 meters. Let's get this straight. A wire of diameter 0.8 millimeters, that means a radius of 0.4 millimeters, you guys. So I would go pi r squared to get the area. Pi r squared. Pi is pi. R is half of the diameter. Half of 0.8. That's 0.4. Pi times the quantity 0.4 squared would give me the area in square millimeters. Yeah, I'd rather have it in square meters, to be honest with you. It's got a length. The length of the wire is 25 meters and has a measured resistance of 1.6 ohms. What is the resistivity of the wire? Well, there's a lot here that can be said. Let's keep it pretty simple. Wrote a little more than this on the notes, but this will work too. Resistivity is rho. Solve for rho. Multiply by A. Right? Here's rho. So get rho by itself. Multiply by A on each side and divide by L. What's going on? Well, I mean, they're saying a lot of stuff. They're saying, they told us the resistance was 1.60 ohms. The area, the cross-sectional area, you guys, the cross-sectional area is going to be pi r squared. Well, what's half of 0.8? Half of 0.8 is 0.4. It's 0.4 millimeters. 0.4 millimeters is 0.4 times 10 to the negative 3 meters. That guy's squared. $25 meters. Yeah, 25 meters, 0.4 times 10 to the negative 3 meters. 0.4 times 10 to the negative 3 meters is the radius squared times pi. I got to make everybody into meters. Meters cancel except for there's meters on top. And there's ohms here, so it's ohms meters for an answer. .217 times 10 to the negative 8. Okay, guys, pretty straightforward. 23. It's a great problem here. 23 is a great derivation, you guys, actually. 23, starting from Ohm's law, show that capital E equals J rho, where E is the magnitude of the electric field, assumed constant, and J is equal to I divided by capital A, is called the current density. The result is in fact true in general. The result is in fact true in general. Okay, so let's erase this. Let's take a look at it. Pretty fascinating question that they're asking, and the answer itself, you know, it's a lot there. I mean, there's a lot there when we look at it. Let's get to it first. I think we're not going to. All right, so again, starting from Ohm's law, show that E equals, starting from Ohm's law, let's just write it down, guys. It'd be the easiest thing. Starting from Ohm's law, prove that. Starting from Ohm's law, let's make sure I'm not blocking the view, you guys. Starting from Ohm's law, show that E equals J rho, where E is the magnitude of the electric field, assumed constant, and J equals I over A is called the current density. The result is in fact true in general. So they're saying that. All right. There's a number of ways to go. Tell you what. We've talked. We've said a couple things already. Let's say them again. I is directly proportional to the potential difference. Yeah. The more potential difference, the more potential for work, the more things are going to be made to move, to flow, and inversely proportional to the resistance. True, I believe that. Delta V, the change in potential, similar to what happened, change in potential difference between two capacitor plates was E times D, remember that? We'll say E times L. An E field applied over a distance, force applied over a distance, there's a lot of ways you can kind of look at it. You could say work is force times distance, let's say. Work divided by charge is F divided by charge times this. This right here is work per unit charge. This is force per unit charge. And you're getting this. So you can argue with it that way. Okay. And we've said a lot of stuff. I mean, we could say, okay, we've put a lot of things here, guys. Let's. They gave us this. We concluded that. That's the same thing I got right here, guys. Same thing. We're trying to prove this. Okay, we're trying to get that to be proven. And said this. All right, we've said a lot. What do we got? We also said that R equals rho L over A. True. Let's talk then. If R equals rho, if R equals rho L over A, then I is delta V over R is the same as delta V over what R is equal to, which is L over A. Trying to argue this with myself. I think I'm thinking too much into this. Take care of this. Well, let's see what we got. We said delta V the change in the potential, it's directly proportional to an E field, and it's directly proportional to the distance that E field is going to be moving something, over which an E field is going to move something. The further the distance I move something across this potential difference, guy, I mean, the further I move something, the more work I've done. So it's directly proportional to the magnitude of E and directly proportional to the distance between the places where this is taking place. If this is taking place over a very large distance, there's a tremendous amount of potential energy associated with that, because it's over a long distance that this is going to take place. This thing's going to get moved. This charge is going to get accelerated over a very long distance. How long a distance? Well, L, whatever L happens to be. But if L is big and E is big, if L is big and E is big, delta V is going to be a big answer. All right. Well, let's take a look. Delta V is EL. Delta V is EL. This guy is rho L over A. Yeah, I'm trying to see here exactly what's going on. Yeah, it looks good to me. The L's cancel, the A comes on top. So the L can't, the L's cancel, and the A gets moved on top, and you got EA over rho. So let's see what that means. For some reason I just want to make sure. Right, okay, that's important. Okay. We do all the song and dance and we get to where we get. Let's talk. Let's go up. Let's move somewhere else. Let's go. Here's I. And we just said I was equal to EA over rho. What do you say? Okay, that's an equation. Yeah, we said it was an equation. Right here we said that was an equation. What you divide by A on each side? Wait a minute. I over A, way over there, is what J equals. These A's cancel. J equals, the two A's cancel. Yeah, this is real big conclusion right here, actually. If there's a big E field, if there's a big net E field, there's a lot of potential. And if that big E field is occurring over a very long distance, yeah, it's even more potential. See, the potential may not be that impressive, so to speak, if this is not something over long distances that we're talking about. This has the ability to accelerate a charge over a long distance. What does that mean? It's going to do a lot of work over a long distance, and there's a big force pushing it. The big force is directly proportional to E, and the long distance, well, force times distance is going to be work. And that's associated with potential energy. That's associated with the potential to do work. So something associated with a big force and something associated with a big force working over a long distance, there's a lot of potential for work to occur. That's a real big conclusion. It's a big conclusion. So it comes out to there, you guys, when we do it. All right, guys, that was 23. Let's go to 31. Pretty standard stuff to look at. It's a bit on the wordy side, but should be okay for us. Problem number 31, they got A and B on that. A 34.5 meter length of copper wire is 20 degrees Celsius. At 20 degrees Celsius has a radius of 0.25 millimeters. 0.25 millimeters, you guys, is 0.25 times 10 to the negative 3 meters. 0.25 millimeters will be converted to meters. You've got to have the SI system of units. 0.25 millimeters is 0.25 times 10 to the negative 3 meters. If a potential difference of 9 volts is applied across the length of a wire, determine the current in the wire. So there's a potential difference, guys. There's an E field associated with it, and there's the whole thing. We got it. I get that. If a potential difference of 9 volts is applied across the length of the wire, determine the current in the wire. That's A. B, if the wire is heated to 30 degrees Celsius, 10 degrees Celsius warmer than what it was, guys, while the 9.0 volt potential difference is maintained. So if the wire is heated to 30 degrees Celsius while the 9 volt potential difference is maintained, what is the resultant current in the wire? Our gut tells us if you heat this thing up from 20 degrees Celsius to 30 degrees Celsius, there's going to be more resistance. Not as much current's going to flow. How much less? We'll have to look at it. We'll see if we can look at it. All right. So 31. How does all that play out? All right, guys, I may have to recharge the batteries on this thing, on the mic. We'll see. Let's see how this thing goes. So tell us about the potential difference. Determine the current in the wire in 2 different scenarios. Nothing else has changed except for the fact that one's at 20 degrees Celsius in one scenario, and at the other scenario, it's at 30 degrees Celsius. And they're asking, okay, well, then figure it out. How are we going to do that? Well, I mean, I think they were talking about it being 20 degrees, right? 20 degrees Celsius was kind of the standard start off on that thing. So if you're going to change, if we talk about the change in resistivity, 20 degrees is kind of the standard. So if T is 20 degrees Celsius minus T sub 0, which is also 20 degrees Celsius, 20 degrees Celsius minus 20 degrees Celsius is 0. It's not going to change what it is. So it comes out to here as far as what's going on here. When they're looking at this, they're saying R sub 0 equals rho L over A, small l. I'm using a capital L, guys. It doesn't really matter. Just watch out. I mean, that's the big thing. What's going on? Resistivity is this. Let me see. Did they actually even tell us that, or do we have to look it up? I think we got to look it up. We do have to look it up. Okay, but we can. They tell us what it is. It's copper, so we look up the resistivity under normal circumstances. And we got a length of 34.5. And we got the area. Here we go. Pi r squared. 0.25 times 10. Tell me that wasn't the diameter, because then I definitely did this wrong. That should be the radius, and it is the radius. 0.25 millimeters. 0.25 millimeters is 0.25 times 10 to the negative 3. We got this. And again, we get some. You're gonna see when you look at my numbers here. I get 2.987 ohms. 2.987 ohms. That's about 3 ohms. So that's that. Great. What's I then? I is delta V over R0, 9 volts, divided by very close to 3 ohms. That's 3 amps. And that's how we do it. B is going to be done the exact same way. And we didn't get caught having to do kind of the fancy stuff we got to do with B. Technically, this is the dynamic. Yeah, this T0 was 20. What's 20 minus 20? It's 0. It's just 1 times R0. And that's the R0 we were dealing with there, because it was 20 degrees Celsius. This one's 30 degrees Celsius for the B scenario. Big difference. 30 degrees Celsius. 30 degrees Celsius, 20 degrees, 30 degrees Celsius, 20 degrees Celsius. 30 degrees Celsius minus 20 degrees Celsius, 10 degrees Celsius, times alpha plus 1 times R0. R0 was about 3, about 2.987, whatever it was. It was close enough to 3. Now, I don't know, maybe sometimes you want to stay a little more accurate, so to speak, until you get the final answer on some of these. And I kind of did on this one, actually. We took this guy. We took the 3, and I said, hey, guys, I do remember it was this. Or at least this is a little more. 1 is 1. The alpha is 3.9. Times 10 to the negative 3. A little bit more resistance. R is 3.104 ohms. That's about 3.1. I equals delta V over R equals 9 volts over 3. What did I say here? Did I write a 3.1? 3.104 or 3.1 here. I got 2.9. There is a difference. There's more resistance, so there's less flow of electricity. And that's how that plays out. All right, guys, let's go to 39. Let's go to 39. Problem number 39 from topic 17. The heating element of a coffee maker operates at 120 volts and carries a current of 2 amps. Assuming the water absorbs all the energy converted by the resistor, calculate how long it takes to heat 0.5 kilograms of water from room temperature to 23.0 degrees Celsius to the boiling point. Okay, there's a lot going on here, guys. We got to be careful. We got to see how they want to play the game here. I think we're still key. I mean, I can look at it. Obviously, the problem's solved. It's been a while ago since I did solve it. But what's going on here? We got to bring this thing to 100 degrees Celsius. Sure. What are we going to do then? Are we going to completely boil away everything? No, it defeats the purpose of making coffee. The lion's share of it has to remain there. So we're not really converting it from vapor. We're not really converting this from liquid to vapor. The heat of vaporization is very, very big because it's hard to take something from a confined state, such as a liquid, and make it into a gas. So that'd be a lot of energy to convert something like that using heat of vaporization. Doesn't look like they're asking that. They're asking you, though, however, liquid to liquid, 23 degrees Celsius to 100 degrees Celsius, from liquid to a liquid at a hot point, but still liquid. 23 degrees Celsius to 100 degrees Celsius. What's going on there? Well, there's current going through there. There's voltage. There's current. There's power being dissipated through the resistor. All that power being dissipated through the resistor goes into heat. All of that heat, we'll say, gets used just for making the coffee. Let's say it one more time. The heating element of a coffee maker operates at 120 volts and carries a current of 2 amps. Assuming the water absorbs all the energy converted by the resistor. Okay, assuming the water absorbs all the energy converted by the resistor into heat, calculate how long it takes. Calculate how long it would take to heat half a kilogram of water from room temperature, 23 degrees Celsius, to the boiling point. Pretty straightforward stuff. Let's take a look at it. Well, I think it's pretty basic. I mean, we're going to see, what's going on here? How does this get done? The idea of power, it's already kind of in the back of our mind on this thing. Power is I squared R. What's that? Well, in this case, the amount of, it's not the Q that we're used to calling Q now. We're calling Q charge, right? In this case, the Q is actually calories or joules of heat energy. So watch out. Watch out on that one. Heat, heat dissipated per unit time is I squared R. Can I write that as the same as delta V squared over R? Can I write that as IV? Yeah. Any one of the above works. Q in this case, and I may have used something, I used E over there. Tell you what, let me stay consistent with my own notes. energy. Doesn't matter. Delta E over delta T. Delta E is probably even a better way to write it. That's not the big deal. The big deal is this. You got this right here, and then, yeah, I just, so I could just easily have used Q meaning heat energy is equal to E is equal to what's going on. How much heat energy do I need to change M amount of mass? Well, if there's a lot of mass, you need a lot of heat energy. It's directly proportional to the mass and directly proportional to the specific heat capacity and directly proportional to the change in temperature. If you want to change the temperature by very, very much, and there's a very massive amount of material whose temperature you want to change very much, it's directly, the amount of heat needed is, there's a lot of mass and there's a lot of heat, if there's a lot of temperature change that you want to get, and there's a lot of mass, it's directly, the amount of heat needed to change mass M is directly proportional to how massive mass M is, and how massive of a temperature change, delta T, do you want to have. So you have this. Uh, 0.5 kilograms. Specific heat capacity is 4,186 joules per kilogram. I want to change the temperature from 23 to 100. That is a change of 77. $161,161 joules. It's a lot. You've got to bring that many joules into, assuming nothing else is happening, assuming this is a situation where energy is not coming from anywhere else, it's not getting lost any other way, everything's straight out going to one place, heating up the water. We're making a lot of assumptions here, but that's the assumptions they want us to make. This is probably the easiest one to use right here, guys, because they gave us they already told us. They're all true. Let's get this straight. Every one of these is true. That's not an issue. Your best bet is that, because that's what they gave you. They gave you all that. That's the power. And that's equal to the power. E over T is power. So what do you got? Well, I times V is going to be joules seconds. Why is that? Because this is Q. This is joules over Q. Joules here. Seconds is on the bottom. This is Q over seconds. Q times work per unit Q is work. It's work per seconds. So that'll get you there. That'll get you there. All right. This is kind of easier done than said, I guess you could say, guys. So let's no more say it. Let's just do it. Equals IV. Here, out of force of habit, guys. You know, I delta V IV. If you're going to call them kind of synonymous, you know, it's watch out. I've kind of reverted back to, this is the potential difference. So write it like that, maybe better. 2 amps, 120 volts, (240 joules per second). Power, that's work divided by time, times time. Work divided by time times time will give you the work. (240 joules per second. Divided by 240 on each side. Divided by 240 on each side. It's all there. It's all there. (671.5 seconds). How many times does 60 seconds go in there? About 11 times and then some. 11.19 minutes. You know, take 60 and divide it into, so that's the answer, guys. I mean, 671.5 seconds, that's 11 minutes point something. For some reason, trying to figure out what this is saying. Yeah, that's right. Right. 11.19. Not 11 minutes, 19 seconds. Nobody said that. It's 11 minutes, 0.19. It's 11.19 minutes. 11.19 minutes. And there we go. Let's go to 49. Problem number 49. Topic 17 again. Chapter 17 or topic 17. Problem number 49. 2 wires, A and B, made of the same material and having the same lengths, are connected across the same voltage source. If the power supplied to wire A is 3 times the power supplied to wire B, what is the ratio of their diameters? See, there are 2 wires, my friends. There are 2 wires here. 2 wires A and B, for problem number 49. 2 wires A and B made of the same material. 2 wires A and B made of the same material and having the same lengths. And they're connected across the same voltage. Despite that fact, there's a power difference supplied to A as opposed to what's supplied to B. If the power supplied to wire A is 3 times the power supplied to wire B, what is the ratio of their diameters? Something's got to be going on here. Yeah, there's more resistance, guys. There's more resistance if something is longer than something else, and it's a different something perhaps. It could be the material offers more resistance, all other things being equal. Well, we're not worried about that. It's the same material. And the length does matter. If it's a longer wire, it's more resistance. All other things equal, if the wire is 10 times longer, the resistance is going to be 10 times more, all other things equal, for a vast array of circumstances. If the wire is twice as long, all other things equal, twice as long, twice the resistance. We get it. But there's not a difference in material here, and there's not a difference in the length of the wires here either. Nor is there a difference in the voltage source. They're both hooked up to circumstances where the potential difference is the same in one scenario, scenario A, as it is in scenario B. They're both hooked up to the same potential difference. They both have the same length. They both are the same material. And yet they're telling us that if the power supplied to wire A is 3 times the power supplied to wire B, what is the ratio of their diameters? It's getting heated up. If the power supplied to wire A is 3 times the power supplied to wire B, what is the ratio of their diameters? 3 times the heat energy is being dissipated in wire A as opposed to what's happening with wire B. Really? Well, the only thing that can be altered here is the cross-sectional area. If the cross-sectional area of one is 3 times the cross-sectional area of the other, that would happen. You'd have to have 3 times the resistance. Interesting. Well, yeah, that's another question in its own right. You know, there is the idea of current, too. How much current's going through there. So I might have spoken too fast on the very last topic that I just brought up. Let's just talk. Might be more to this than meets the eye. Depends how they're asking the question as well. They may be allowing certain assumptions to be made. Let's see. Let me take another look at this, guys. They want to know what is the ratio of their diameters. And it's not as obvious as you might think. If the current going through the two was the same, it's an interesting dynamic, but they're not saying that. They're saying that the power is 3 times that. So let's see what's going on here. What's basically going on is, guys, this stuff's a little easier. Again, like so much of the other stuff, this stuff is easier done than said. The basic, we're assuming the temperatures aren't varying either. R is rho L over A. Let's talk. The length L is the same as the length of wire A is the same as the length of wire B. They're equal. Rho is rho A, rho B. It's the same material, guys. I already said that. We already said that. V, or delta V, is V sub A, V sub B. It's the same Same potential across both. We got to talk. Wire A is getting more power. If the power supplied to wire A is 3 times the power supplied to wire B, what is the ratio? The power going through A power going through A, power going through B, isn't that the same as sorry guys, I need more chalk. IA, VA, I times the potential difference, okay, we talked about that. Remember what we said, this is this is coulombs per second. This is joules per coulomb. Joules per coulomb times coulombs per second is joules per second. This is joules. This is joules per coulomb. This is coulombs per second. Coulombs and coulombs cancel. You got joules per second. If VA and VB are equal, that guy right there, and they told us the ratio of the power is 3 to 1. Fantastic. So we got it to there. A lot going on here, guys. We will have to say this then, that IA equals 3 IB. True. What does that mean? Well, that means that IA is V, potential difference, divided by R, and that's IA. And this guy, that's equal to 3. IB is V divided by the resistance going on with B. That's the key. That's the key. Once you got to here, IA equals 3 IB. Once you got to here, guys, IA equals 3 IB. IA is V over R, associated with the resistance at whatever that one is. You can put an A right here if you want. I'll say R is the resistance of wire A. R is the resistance of wire A. RB is the resistance of wire B. V over R is IA. V over RB is IB, but you got to multiply by 3 to get equal to that one. That's pretty crazy. Divide by V on each side. multiply by RB on each side. There's a lot of ways to write it. I didn't write the A here. I maybe should have. Whatever. That's the A. Multiply by RB on each side and divide by V on each side. RB, RA. That's huge. According to this, that would make sense. Because V squared over RA is three times bigger than V squared over RB. The V being the potential difference. The V being the potential difference. Maybe this would have even, I don't think I went this way on my notes. I may have later on. I'm looking right now. As I'm doing this, I'm looking, guys, but this is also a way you could have done it. Cancel the V squareds on each side, multiply by RB, looking good. Cancel the V squared over there, cancel the V squareds on each side, divide by V squared on each side, and multiply by RB on each side, and you got the same thing you got here. What does that mean? Well, it means there is a rho L over A sub B. This is rather pretty fascinating stuff, actually. Yeah, and it works. I'm just trying. I'm second guessing myself a little bit here, guys, but probably should not. Yeah, there's a lot more current going through the wire that's got more heat, but its resistance isn't as much. No, but it doesn't have to be as much because the I squared kind of compensates for that and still makes it become more. So what do we got, guys? I mean, let's talk. There's got to be a B here. There's got to be an A here, and the ratio is 3-to-1. It's kind of crazy. It's kind of crazy. The other one's got more resistance. This one's got more resistance. You think more heat would be dissipated because it's got more resistance. No, because there's less current flowing. There's less current flowing for that resistance to actually be able to generate a very large amount of energy. Certainly the one that doesn't have as much power that it's giving forth, you think it would have as much power or more because it's got bigger resistance. Yeah. It's got more resistance, but it has less current. This guy's got 3 times the current than that one has, and when you do that, when you're comparing the two, the powers, you're comparing, I squared RA over I squared RB. This guy's got 3 times what he has. That's 3IB. RA, you can play this a whole bunch of ways, I guess. If you multiply by RA on each side and divide by 3, RA is RB over 3. Down here, you got IB squared RB. Wait a minute. Square the product 3IB. Square the product 3IB. That's 9IB squared times RB over 3. And the other one is IB squared RB. Wait a minute. The 9 and the 3 cancel. You got 3 the bottom, you got it makes sense. The power being brought forth by wire A is indeed 3 times. That happens even though the resistance at IA is, let's see here, yeah, even though the resistance is 1/3 of what it is at RB. Even though RA is 1/3 of RB, still it brings forth more power because there's so much more current, or the current squared takes it further. So all that makes sense, guys. All this falls in line. I mean, all this, makes sense. What's going on here, guys? The rows cancel. The L's cancel. The AA goes on top. The AB goes here. There it is. AA over AB. For some reason, I'm not even confident that should be the case, though, is it? Yeah, it's about right. Yeah, it's absolutely right. What are we talking about? Pi RA squared. Pi RB squared. The pi's cancel. Square root both sides. Let's make sure which one we're talking about now, guys. What is the ratio of their diameters? Same thing. Aren't diameters just double the radius? Aren't diameters just double? Multiply by 2 over 2 on this side, multiply by 2 over 2 on this side. Heck, just multiply by 1 on this side, called 2 over 2. You got 2RA over 2RB is the square root of 3. Diameter of A over the diameter of B is what this is. Square root of 3 over 1. I wrote it lowercase d. I wrote it with a lowercase d. Lowercase d equals, lowercase d sub a over lowercase d sub b equals the square root of 3. The diameter of A is the square root of 3 times bigger than the diameter of B. And that's the story on that one. Like I said, I wrote it a little different. I don't think anybody's going to make a big deal out of that, guys. I mean, but the thing is, the symbols are fine. You got a lot of flexibility with the symbols. Most teachers are going to be fine with that, as long as you don't do anything too outrageous and as long as you're getting the right answer. The big thing is you know what you're doing, or you're getting the right answer at the end. Symbols are negotiable. Not knowing what we're doing, if I don't know what I'm doing, that's not negotiable. If we don't know what we're doing, that's going to be an issue. Same dynamic, guys. Same thing. Neat problem. All right, guys, go to 55. And again, there's the last two. We got the last two problems to do here, guys. 55 and 63. Let's see how it proceeds. It's probably a lot. I'll try to go a little bit faster if I can, guys. But there's always a little bit of a compromise you got to make. You want to make sure people understand what you're doing as well. Problem number 55. A particular wire has a resistivity of 3.0 times 10 to the negative 8. A particular wire has a resistivity of 3.0 times 10 to the negative 8 ohms times meters, and a cross-sectional area of 4.0 times 10 to the negative 6 meters squared. A length of this wire is to be used as a resistor that will develop 48 watts of power when connected across a 20-volt battery. What length of wire is required? Okay, pretty standard stuff. It's a little more. It's more wordy, I guess, than it is challenging, I guess you could say. All right, guys. We've said a number of things before. Let's say it again, I guess. Some of them, at least. Okay, I'm using the V to mean delta V in this context. Just look at the context in which we're speaking, guys. Whatever's easier. To me, it's a little bit easier to write it like that in some context if you're trying to write a lot of stuff. But again, it's got to work for you. I make sure this is working for you guys. All right. There's a lot they're saying here. I think they're saying enough that this is probably the ticket right here, guys. Let's see what we can say here. We can go here. And that V is synonymous with this. at least within this context, at least within this communication in which we're talking. So we got this right here, which is equal to what? Basically, what it, so what's that? So what's going on here? Let me just try to speak their language, guys, as much as I can. Let's look at it. From that right there, is it true? We can write it like that, as we said. If that's the case, it's the junk we were talking about earlier, guys, right? We're talking about something like this from early on. And, what does that mean? Well, it means a lot. I mean, rho is really on top, so it's really like rho L. And the A VA squared or rho, there's a whole bunch of things you can say here, guys. So what are we saying? What is this? Power equals, that's the delta V squared. We'll just call it V. Put the A right there. Here's rho, here's L. We're looking good. Why don't you multiply by L on each side and divide by P? Sounds good. I think we're done. I mean, once you get to here, they're telling us, they told us a lot of stuff. So let's make sure we're speaking the same language here that they are on this. They gave us the resistivity, that's 3 times 10 to the negative 8. They told us the cross-sectional area, that's 4 times 10 to the negative 6. Both are in SI units. 48 watts is the power. And it's a 20-volt battery. Hey, it's all there, guys. It's all there. It's all there in the units we want, too. 20-volt battery. All our SI units. We're not in trouble here. We don't have to do anything. The power is 48 watts. That's an SI unit, too. That's joules per second. Whatever. Keep going, keep going. Do that division. You're trying to find what L is. L 1111.11. 1111.11 meters. That's about 1.111 kilometers. They kind of made it about equal because they cut it off a little bit, but it's not a big deal. And that happened right here. And the big thing is you got it about here. How'd you get it here? It's V squared divided by R. But what's R? It's rho L over A. V squared divided by rho L over A is rho L on the bottom and the A comes on top. It's right here. So you got to get to here. Once you get to here, it's academic. You solve for L, as we did, and it'll give you L right here. Let's go to 63. All right, guys, pretty straightforward, pretty easy on this one. For number 63, a length of metal wire has a radius of 5.00 times 10 to the negative 3 meters and a resistance of 0.100 ohms. When the potential difference across the wire is 15 volts, the electron drift speed is found to be 3.17 times 10 to the negative 4 meters per second. On the basis of these data, calculate the density of free electrons in the wire. We got kind of that one master equation that kind of gets us through the whole thing, and it shouldn't be an issue for us at all. Should not be an issue for us at all. So what's going on here? How does this work, given what they've told us? Well, we know a lot already. $63 is that. Let me write it first. Sorry about that, guys. 63 is this, essentially, based on things we've already talked about. You know, they've said a few things. Somewhere else I wrote something a little different, which I don't even think I need, to be honest with you. You know, in my notes, guys, I have R equals rho times L over A, which is certainly true. But R equals rho times L over A, but I think they gave us everything that we need right up front. They didn't tell us anything about a rho. They didn't need to. They told us what the resistance was right up front. So we don't even need to use. This is true. I have it in the notes, and it's certainly true, but we don't even need it. We got this right here. They're asking you what N would be, and the way you're going to figure out N is get N all by itself. Just that. Now wait a minute. They just told us right up front, basically. Well, no, they didn't tell us up front. Forgive me, they did not. We know that I is the rate of flow of charge. And that's delta V over R. It's a 15-volt battery that's connected to it. 0.1 ohm, 15-volt battery, 0.1 ohm resistance, 150 amps. True. Not done, but true story. Make sure all the units agree with what they're supposed to agree with. They got to be the SI units. If they are, just plug in the numbers, you're okay, if they are the SI units. Q is every electron (1.6 times 10 to the negative 19). They gave us the drift speed. Yeah. What's the cross-sectional area? Well, cross-sectional area is pi r squared. Pi is pi. They told us 5 millimeters. They didn't tell us 5 millimeters. They made it easy. 5 millimeters is 5 times 10 to the negative 3 meters. 5 times 10 to the negative 3 meters is what the radius is. Right. So they gave us everything up front, guys. They almost, the challenge in this problem is don't make a careless mistake because they told us everything. That's it. You're going to grind that out and get the answer. It's as simple as that. You got to run through the whole thing, obviously. You got to get an answer for, the whole bottom thing, right? All the way to here. Get that. That's it. Three point 3.765 times 10 to the 28th charge carriers per cubic meter. Yeah, that's how many electrons. I mean, the way they asked it, they're assuming they're all just electrons by themselves. On the basis of these data, calculate the density of, on the basis of these data, calculate the density of free electrons in the wire. Here they are. These are the free electrons in the wire per cubic meter. All right, guys, thank you so much for your time. All the best. We'll talk again.